Let's talk about nuclear power. On one hand, it could be one of our most powerful weapons against climate change, but on the other, a lot of countries are actually shutting their plants down. So what gives? Today, we're going to dive into the complex, pretty controversial, and honestly fascinating future of nuclear.
All right, let's just start with a single number to frame this whole thing: 50 gigatons. That's how much CO2 nuclear power has prevented from entering our atmosphere in the last half-century. Now, to put that into perspective, that's like hitting the delete button on 2 entire years of global energy emissions. That's huge.
So that brings us to the big, obvious question. If this technology is so good at fighting climate change, why are so many countries hitting the brakes? It's a real paradox, and if we're going to understand where nuclear is headed, we have to get to the bottom of this hesitation.
And to figure out where nuclear is going, you gotta look back at where it's been. Specifically, the accidents that have really defined how all of us think about it.
Think about 3 Mile Island back in '79. This wasn't some single big explosion. It was more like a slow-motion train wreck, a cascade of tiny failures. First, a filter gets clogged. Simple enough. Then, a relief valve gets stuck open. Then, it turns out a backup system was never turned back on after some routine maintenance. And the final piece of the puzzle? Pure human error. An operator completely missed the warning lights. And get this, one theory is that his own stomach was literally blocking his view of the control panel. It just goes to show how a bunch of small, almost boring mistakes can spiral into a partial meltdown.
Now, Fukushima in 2011, that was a whole different beast. It started with a massive earthquake, and then a tsunami that just completely swamped the plant. It knocked out the main power grid, and critically, it knocked out the backup generators too. And that revealed the Achilles heel of these old designs. The cooling systems needed electricity to work. No power, no pumps. No pumps, no cooling. A meltdown at that point was pretty much baked in. So you look at these two disasters, and you start to see a pattern, a couple of really big fundamental problems. First, these old reactors rely on active cooling. They need power, they need pumps, they need people. Second, they use high-pressure water as a coolant, and if things go wrong, that can lead to dangerous steam explosions. And on top of all that, you've got the waste problem, an open fuel cycle that creates this nasty radioactive stuff with no real permanent home for it, at least not in places like the US. But here's the thing about failures. They force innovation. They sparked a total engineering revolution. Scientists and engineers looked at these exact problems and started designing a whole new generation of reactors to solve them. And that brings us to Generation 4 reactors. Around the early 2000s, this international forum got together and said, okay, let's start from scratch. They had 3 big goals: make them ridiculously safe, produce way less waste, and make them a whole lot more efficient. Now, the real game changer at the heart of these new designs is a simple but brilliant idea: get rid of the high-pressure water. Instead of water, they use things like molten salt or liquid lead or even gas as a coolant. This lets them run hotter, which means they're more efficient. But, and this is the key, they operate at normal, everyday atmospheric pressure. That is a massive, massive upgrade for safety. And this new approach unlocks an almost magical safety feature, one that's just built into the laws of physics. With some of these designs, like molten salt reactors, the reactor pretty much takes care of itself. It all boils down to this one incredible principle: the hotter it gets, the less fission occurs. Let me show you how that works. It's called passive safety. It doesn't need a computer or a human to flip a switch, it just happens. So if a molten salt reactor starts to overheat, the hot liquid fuel literally expands. And as it expands, the atoms get farther apart and the nuclear reaction automatically slows down. It's self-regulating. And if for some reason it still gets too hot, there's a plug at the bottom, a freeze plug, that's designed to melt. The fuel then just drains by gravity into safe holding tanks. The problem literally solves itself. No drama. I mean, when you put them side by side, the difference is just night and day. Old school reactors, high pressure, high risk of steam explosions. These new molten salt designs, low pressure, basically zero risk. The efficiency gets a huge bump too. But the real headline here is the shift from active safety, which needs power to work, to passive safety, which is just governed by physics. It's a total paradigm shift. Okay, so the engineers have basically cracked the safety code. Problem solved, right? Well, not so fast, because that still leaves the biggest, oldest, most stubborn hurdle for any kind of nuclear power: the insane cost. And that's where the next big idea comes into play.
This is the big idea behind small modular reactors, or SMRs. The concept is to stop building nuclear plants like these giant, custom, one-of-a-kind cathedrals. Instead, let's start building them like we build airplanes, small, standardized, and mass-produced on an assembly line.
And the promise here is enormous. If you can build them in a factory, you get economies of scale, which should slash costs. Simpler, standard designs are inherently safer and way faster to build. And because the core is smaller, it's actually even easier for them to cool down passively. It sounds like the perfect solution, right? A total win-win-win.
So this all sounds like a complete game changer. And, it could be. But even with these brilliant, safer, smaller designs, we come crashing right into nuclear's oldest and most powerful enemy. So let's just remember, the whole economic model of SMRs, the entire business plan, hangs on this one single idea. Mass production in a factory will make them cheap. But here's the catch. To build a factory like that is going to cost billions of dollars. And you have to ask, who in their right mind is going to spend billions on a factory when they don't have a single guaranteed customer lined up? And then you flip it around. What utility company is going to sign a multi-billion-dollar check for a bunch of reactors from a factory that doesn't even exist yet and can't prove it can deliver on those cost savings? It is the ultimate chicken and egg problem, and it has pretty much paralyzed the entire industry. And this isn't just a theory. You can see it playing out in the real world, right in the price tag. Right now, onshore wind and solar can churn out electricity for about $30 a megawatt hour. NuScale, a leading SMR company, was originally aiming for $55. But thanks to delays and rising costs, their newest estimate is up around $100. They're just not in the same ballpark anymore. So it doesn't matter if we're talking about the giant old-school reactors, the futuristic Gen 4 designs, or these promising new SMRs. They all keep hitting the same brick wall, the cost. It's either the massive upfront investment, the lack of funding to develop new tech, or this chicken and egg problem for SMRs. Cost is the common denominator. And all of this seems to point to a really tough but important conclusion. When it comes to a technology this important for our energy security, for our climate, this just might be a problem that the free market on its own cannot solve. And so that's the final massive question we're left with. As our energy needs keep growing, as the climate crisis gets more and more urgent, should governments be the ones to step in? Should they be the ones to make the huge investments needed to break that logjam and kickstart this industry? Not for profit, but for strategic reasons? Should they be the ones to decide nuclear's future because the market can't seem to figure it out?